Not every project has access to the weather research and forecasting outputs or high-performance computing resources. In many cases, especially at the feasibility stages, analysts use spatial interpolation to generate high-resolution surfaces from sparse data or low-resolution grids. The simplest method is inverse distance weighting, which estimates values at unknown points as weighted average of nearby known values, with weights decreasing as distance increases. It is quick to compute but lacks statistical robustness. A more sophisticated option is kriging, which incorporates spatial autocorrelation. It models how a variable changes with distance and provides not only interpolated values but also prediction uncertainty. This is especially useful in risk-aware energy planning. Spline interpolation fits a smooth mathematical surface throughout the data, minimizing curvature. This is effective for smoothly varying variables like temperature or irradiance, but can misrepresent sharp transitions. These techniques form the backbone of statistical downscaling when applied to climate model outputs. For example, interpolating long-term wind speed trends or downscaling future temperature scenarios using point-wise regression and spatial smoothing. Best practice involves validating the resulting surface against in-situ measurement or cross-validation. The reliability of downscaled surfaces depends heavily on data density and method assumptions. After producing high-resolution meteorological surfaces, whether through the weather research and forecasting model, kriging, or regression, the next step is visualization. Good visualization does not just present data, it helps reveal spatial patterns, communicate uncertainty, and support planning decisions. Key principles include using appropriate color ramps, clarity in legends, and meaningful classification schemes such as quantiles, natural breaks, fixed thresholds. Avoid using rainbow color maps or too many categories. Maps should also be contextualized. Overlaying infrastructure, for example grid lines, administrative boundaries, or exclusion zones, turns a raw meteorological surface into an actionable planning tool. When temporal dynamics are important, consider using animations or interactive visualizations. For example, show seasonal wind patterns or animating radiance across the year. Ultimately, visualization is about storytelling with spatial data. A good map helps not only analysts but also decision makers, stakeholders, and the public understand what the data means and what actions it supports. In this final module, we bridge the gap between global climate data and local energy systems. We explored the limitations of coarse resolution models and how downscaling techniques allow us to work meaningfully at the spatial scales required for clean energy development. From statistical tools like kriging to fully physical simulation with weather research and forecasting model, you now have a framework for understanding, evaluating, and using downscaled meteorological data. This knowledge will allow you to assess wind and solar resources, model thermal demand, and support infrastructure design with greater spatial intelligence. As energy systems become more decentralized and as climate risk demand final scale planning, your ability to interpret and generate high-resolution climate data will become increasingly central to your work.